Okay, I'll wait for a few minutes and then I'll start. Okay. I'll wait for a few minutes and then we can start. Okay. Uh, so, so if you have any question, you can ask, or else I'll start with the quantum anomalous Hall effect. Okay. So, in the last class, what we are trying to understand is that the anomalous Hall effect. Okay, so the anomalous Hall effect was a Hall effect or a component of the Hall effect without the magnetic field, which doesn't scale with the applied magnetic field, rather it scales with the magnetization of the system. And as we are trying to understand that, one of the key components for understanding the anomalous Hall effect, sorry, was the Berry curvature. And those that Berry curvature actually modifies the semi-classical or the velocity expression actually. Okay, so usually we have this kind of velocity expression for the electrons or the holes in the solid periodic system, but this is just the band velocity. Okay, so if for example, if I have this kind of band, then so if I have this kind of band, then the band velocity is just simply the derivative of it, right? So this represents the slope of this curve as a function of uh, momentum. Okay, so at each point your slope is changing, so the velocity is also different, and so on. So that was the previous notion that the electron's velocity is primarily determined by the band velocity. But then with this topology and wave function geometry consideration, what we have is that there is another term which is related to the Berry curvature, right? Which is called Berry curvature, and so this give rise to a transverse velocity whenever you apply electric field in some ferromagnets actually. And this term or the anomalous Hall current arising from the Berry curvature are only finite for the magnetic materials, which breaks time reversal symmetry. And what we have done is that explicit symmetry analysis, at least under time reversal symmetry and spatial inversion symmetry, which essentially lead us to the following conclusion that in non-magnetic system where time reversal symmetry is preserved, the omega, the Berry curvature at k point, if you take time reverse partner of this particular Berry curvature under time reversal symmetry, it will go to the minus of omega of minus k. Okay, so suppose you have the whole Brillouin zone. You are saying this is one point in the k space. This is let's say kx, and this is ky omega of k. This particular point. Then what this time reversal operator will do is that it will make at minus k, okay, and the omega, the Berry curvature at this particular point is going to be negative of this particular value, okay. So the value is also getting reversed. I mean, the value picks up a negative sign as well as the momentum point, of course, goes from here to here as we operate time reversal symmetry. And because of this particular symmetry, whenever there is a time reversal symmetry present in the system, what happens is that the whole integration of the Berry curvature in the whole Brillouin zone, it actually identically vanishes at each point. Okay. This means that there is no anomalous Hall effect in non-magnetic system. However, if the time reversal symmetry is broken, which is the case for magnetic materials, this particular symmetry condition doesn't hold. Okay, and this leads to this breaks the cancellation of the Berry curvature, integration of the Berry curvature in the religion, so that it can be non-zero. Okay, so any non-zero value it can take continuous non-zero value. Uh, and as a result, you will have I mean, conductivity, transverse conductivity rather, because there is Levi-Civita tensor. So any Levi-Civita tensor, whenever you have two spatial component A, B, and C, whenever any two of them are same, this is going to be zero. This part is zero. That means the sigma AB will also be zero. So the purely transverse part, for example, YX component can be non-zero when there is time reversal symmetry broken in the system. Okay, and that explains that in ferromagnetic materials, the anomalous Hall effect can be finite, which was the case that Lorentz himself, Edwin Lorentz himself observed in 1881. Okay, for almost 70 years, there was no explanation, maybe more than 70 actually. The 1954 Karplus and Luttinger gave some argument, not based on Berry curvature, but based on scattering and so on, which later people connected again to the Berry curvature. Okay, so this Berry curvature thing is the key to understand the anomalous Hall effect, and you need ferromagnetic material. So that was the previous class recap. So what we understood is that there can be anomalous Hall effect in absence of magnetic field in ferromagnetic materials. And we are not, or we have not commented anything about that this Hall effect will be quantized or non-quantized and anything, right? You just have some value of anomalous Hall effect, and that's it. It turns out that there is a quantized version of the anomalous Hall effect as well. So in previous few classes, what we were trying to understand when we talked about the quantum Hall effect, what was the our goal was that in conventional materials rho xy versus b you plot it is linearly increasing, but then in some two-dimensional materials people observed in 1981 I think von cleansing that okay, it increases rho x y increases with the magnetic field up to some magnetic field, but then as you increase the magnetic field there is a quantization plateau that develops. Okay. So this was this plateau which we wanted to understand when we are trying to understand the quantum Hall effect. And these are the quantized plateaus. Okay. Now what we are trying to understand is the following, that you have a in ferromagnetic materials, once you plot this rho xy versus V, then of course you will have increase in the conventional Lorentz force effect, but then after a certain point it's kind of saturates. Okay, looks like something like this. It's not exactly saturating. It's not like a flat, but then slowly it saturates, and this doesn't definitely scale with the magnetic field. Okay, so this part you can think of. So this part, let's say, up to this part, you can think of that this is directly proportional to B rho xy, but then this particular part is not really proportional to B, right? Once you decrease the magnetic field, what really happens is that it actually doesn't go to zero. Okay, so instead of going back to this path, rather it follows something like this. So it will come back and then somewhere here. Okay, so you are getting rho xy b equal to 0. So this part is b equal to 0 is not equal to 0. So some finite transverse resistivity. And if you do the full step, meaning you, let's say you want to be some b0 value, okay, and then you come back here minus b0 and you will trace the same thing, you will almost see a very good hysteresis like feature depending on the sample to sample. It varies, but as we know that in ferromagnetic materials, magnetization versus magnetic field shows this kind of hysteresis curve, right? So this was our understand, our aim to understand. So this part we call anomalous Hall effect. So this Hall effect, so rho xy at b equal to 0, whatever it is, the value, it is called anomalous Hall effect. Okay, but there is no quantization story so far. It turns out that there is it can be quantized, okay, and uh, remarkably unlike the experimental case of quantum Hall effect. So this was the case of quantum Hall effect, and this is the case of anomalous Hall effect. Okay, so the quantum Hall effect was first observed in experiment by von Klinging in 1981, okay, or 82 actually. Uh, this is the, I think the paper was published in 82, but it was submitted in 81. So this was, so both of these phenomena, the Lorentz Hall effect, which says that your resistivity should go linear, and the quantum Hall effect, which found that no, these are quantized under very high magnetic field, very clean sample. Both are experimentally initially observed, and then subsequent theory came, and people understood how things works. But the story of anomalous Hall effect is a little is also similar. Okay, the story is, so far is similar, that people observed a linear, Lorentz Hall effect, and then in ferromagnetic materials, Lorentz himself observed that there is a finite rho xy at p equal to 0. But when it comes to the quantized version of anomalous Hall effect, it was actually initially theoretically predicted. Okay, so this was predicted in I think 1988 Yeah, I think 1988 by Haldane. So what he did is that, and this was the time during when people were really trying to understand the quantum Hall effect, and there was much study about quantum Hall effect. But people knew about the anomalous Hall effect. What Haldane proposed is that quantized version of anomalous Hall effect. Okay. So what he did is that he said that okay, there is anomalous Hall effect whenever time reversal symmetry is broken. He cooked up a model which now we know as Haldane model based on graphene itself, and he said that okay, there can be quantized anomalous Hall effect, meaning the sigma xy or yx anomalous Hall can be in units of e square by h actually. Okay, and these are some quantized number. Let's say c. C can be 1, 2, and so on. So this was the prediction, and later people observed in many materials actually. I think Bi2 Ac3 is one such material, and then people observed other materials also. Recently, MnBi2T4 is one of the example people are interested about. Okay. So mostly I'll try to explain what do we mean by quantum anomalous Hall effect and what explains this. And if time permits, I'll go to the quantum spin Hall effect. Okay. So the model Haldane considered is the following. That so so the model breaks time reversal symmetry, and this is one of the fundamental symmetry relation we need because we have observed that if time reversal symmetry is preserved, then there is no anomalous Hall effect. Forget about the quantization of anomalous Hall effect, right? So it breaks time reversal symmetry. But then we are not allowed to apply any magnetic field because then it is not anomalous Hall effect. It's just an all Lorentz Hall effect or the quantum Hall effect. So we are not able to, I mean, we are not allowed to apply any magnetic field. So the way Haldane cooked up this model is that effectively there will be a staggered flux. What do we mean by that is that overally, so this is let's say my graphene lattice or one unit cell rather. So then what he assumed is that so these are let's say A type atom and these are B type atom. And then okay. So whenever there is so the nearest neighbor hoppings or rather yeah. So so what he assumed is that whenever there is a next nearest neighbor hopping, for example, this to this, A to A, and I mean, or B to B is also allowed. They picks up a phase, extra phase, and then that extra phase is arranged in such a way that overally the effect is not there, but then you add in such a way that I mean B to B there will be +5 phase, and then A to A, let's say there is a -5 phase, and so on. So if we represent it in terms of Hamiltonian, then can write. So let me write few lines actually, then I will write the Hamiltonian. So the idea is to introduce a magnetic field that is 0 on average. Okay, on average. So you are kind of introducing local magnetic field so that overall this is 0 because this needs to be 0 because we are not applying any external magnetic field. And yeah, so whenever we have local magnetic field or even global, but in our case it is local. So through the Pyle substitution, and this is basically a Paul substitution means you'll have Aharonov-Bohm phase. Okay, and this actually leads to complex next nearest neighbor hopping. Okay, and what this essentially means in our case, this particular figure is that there will be hopping which are e to the power I phi gamma prime, where phi is positive. So the hoppings, next nearest neighbor hoppings are, let's say, given by this e to the power I phi gamma prime, where phi is positive, let's say, for hopping in clockwise direction, and phi is negative for anti-clockwise direction. Okay. Okay. So then the Halden's model is given by the following. So Halden's model that he wrote is gamma 0. These are nearest neighbor hopping as usual for graphene. So Ci dagger, sorry, Ci daggers, Cj, and then lambda t. So the double bracket means the next nearest neighbor hopping. E to the power I phi ij. Phi ij is dependent on the ij because it tracks that if the hopping is in the clockwise or anti-clockwise direction, and depending on that, we'll have a sign change. Again, Ci dagger, Cj, and we can have the mass term on-site potential. Okay, so yeah. I. So these are on site. So this is only summed over each carbon atoms. Okay, these are not summed over Ij combination because these are on site. So there will be Xi actually and Ci daggers Ci. Okay. So this was the Hamilton. So this is the conventional next nearest hopping. Sorry, nearest hopping, and this is the next nearest neighbor hopping, next NN, and this is on-site potential. Okay. So what it does is that this is the conventional term. It does nothing. It gives just the graphene bands with the Dirac touching point, and this gaps out. So this term gap creates gap in the spectrum in spectrum, and this also breaks p symmetry, inversion symmetry. Okay, and the easy way to see is that this delta potential, this xi term is so this xi is the Valley index. So for example, so this is one of the values. Let's say in the case space, these are the each sublattice corresponds to one of the values, loosely speaking. So for one value, let's say I equal to plus one, then the overall potential is delta. So here let's say it is delta. Then xi equal to minus one, that is the another value, that means the B type of atom, let's say, then it will be plus delta or the minus delta, vice versa. So two atoms, and we know that the graphene, the brilliant zone consists of two atoms, something like this. So the two atoms in the brilliant zone experiences different potential. So this breaks the time reversal, sorry, parity symmetry or the inversion symmetry of the model. Now this term breaks the time reversal symmetry. The next nearest neighbor, complex hopping, breaks T symmetry. Remember that we have not effectively included or introduced any external magnetic field. Still, it breaks time reversal symmetry. Okay, and that's how the model was introduced. So this was just a model to understand or to predict that there can be a quantized version of the of anomalous Hall effect, and later it was indeed verified. This model was exactly not realized, but then other type of system was introduced, not in graphene but other systems. Essentially, the idea basically worked out. Okay. Okay, so I'll not make this, this lecture too much mathematics oriented, but rather explain the key logic. Okay, okay. So this was the model introduced, and then if we uh, sort of do in the case space, so this is the real space model. Okay, so this is a Hamiltonian in the real space, and it is a tide binding Hamiltonian. Okay, so if we go to the momentum space by Fourier transforming this, then what we can do, what we will get in terms of Hamiltonian is the following. So essentially we have this kind of structure in our mind. So let's say this is graphene Brillouin zone. Let's draw a few more. Okay, so what we have is the following. So this is, let's say, B1 reciprocal lattice vector, one of the reciprocal lattice vector, and then let's say B2, and let's call this to be B3. Okay, and the real space vectors, these are A1, A2, A3. Okay, the just nearest neighbor vectors are A1, A2, and A3. Whereas, so these, if you notice that these B1, B2, and B3 are representing the next nearest neighbor vector, right? That is because, so this is my nearest, but then next nearest neighbor is somewhere here, right? So this is B1, again along this direction also same. So this is my nearest neighbor connected by this bond A2, A2 vector, and then B2 represents the next nearest neighbor. Similarly here also. So this is the next nearest neighbor. So for this kind of system, so the momentum space tide binding Hamiltonian, it can be written as, so you were just doing the Fourier transform of this Hamiltonian, nothing else. Okay, so the Hamiltonian as a function of k then is given by gamma. Yeah, we have written gamma 0. So gamma 0, sum over I, let's say I goes to nearest neighbor, cos over k dot ai. Ai are these a vectors drawn in this figure. Okay, which is sigma x associated with sigma x, and then plus sine of k dot ai sigma y and then plus 2, we wrote gamma prime or what? Okay, so let me write just gamma prime. So gamma prime cos phi, I goes to next nearest neighbor, okay, triple n, cos of k dot bi, because bi connects the next nearest neighbors, and then so this is associated with sigma 0 identity matrix, and then the gap term is delta minus 2 gamma prime sin phi, again I goes to next nearest neighbor, sin k dot pi, sigma z. Okay, okay. So this is the Hamiltonian of the Haldane model in the K space. Okay. Now, so this is a complicated Hamiltonian consisting of cosine and sine functions uh, in the momentum space. Now, if we go to the low energy, so in the low energy limit, that is to say that your the energies are you are essentially around looking at energy nearly equal to zero. Okay, where your k a are very small. Okay, so k is much less than one. So yeah, so in this limit, so what you can replace is that so this kx, ka and kb are there, right? So this you will use this limit. If you use this limit, and of course the fact that cosine of x is nearly equal to 1 minus x square by 2, and then sine of x is x minus x cubed by 3 factorial when x is much less than 1. You will essentially keep only the first term, okay, 1 and x in cosine of x and sine of x respectively. So if you do this extension, or I mean the limit of this Hamiltonian, then what we can get is the following. So depending on the it is k Hamiltonian or around the k value or k prime value, you will have a Hamiltonian of something like this, minus plus 3 gamma 0 by 2 kx sigma x plus ky sigma y plus delta plus minus 2 gamma prime cos phi sigma z. Okay, so this is the low energy Hamiltonian. So this is I mean, very interesting and important because then we can do exact calculation of Berry curvature and so on. Whereas in the tight binding calculation, you cannot do things analytically. It's a very complicated cosine function and sine function, right? Okay, so with this low energy Hamiltonian, what you can do is that you can construct, I mean, you can calculate the Berry curvature. Okay, so remember our goal. We are trying to understand, is there any quantized Hall effect in the system? Right? Anomalous Hall effect rather. And so this is a gap graphene model actually because sigma z is there, so the spectrum will be gap. So if this particular part where I mean the associated with the sigma z part, if it is not there, then this part is essentially just a linear in momentum, right? So this part will look like something like this. Okay, but the moment you have sigma z, your band starts looking like this. Okay, so there is some finite gap. Okay. Okay. Now, what Haldane proposed is that in the gap also, So even if you are in the gap, let's say your Fermi energy lies somewhere here, okay? In the gap, you will have the conductivity sigma xy or yx anomalous Hall to be quantized in units of E square by h. This is exactly like the uh, this is exactly like the quantum Hall effect where you need to apply an extra magnetic field to get quantized response. But here you don't need to I mean apply an extra magnetic field. Rather, your time reversal symmetry in the system is broken. Okay. In the earlier case, the quantum Hall case, the time reversal symmetry was being broken by the applied external magnetic field, right? But here you need in system needs to break time reversal symmetry without any magnetic field. Okay. Okay, so what our goal is to find that if we calculate the sigma xy, which is minus e square by h epsilon, this is let's say AB, ABC, uh, sum over all the k points or integration over k, and this is the Berry curvature, which is again a function of k and d2k. So whether this quantity comes out to be integer, is it integer, right? So if it is integer, then we are sort of established that okay, there can be quantized anomalous Hall effect, right? So if this is not zero, then you are already sort of know that this is anomalous Hall effect. But if it is not zero and it is not only not zero, but then also quantized. So see some quantized number, let's say, and see units of E square by h, then it is quantum anomalous Hall effect. Okay. So this quantum is associated with this C. Okay, okay, and it turns out that C is just the Chern number. Okay, just the integration over this Berry curvature. Okay, so what we need to essentially need to do is that calculate the Berry curvature explicitly, right? So I'll state the result and explain the things. So for any general 2 by 2 Hamiltonian, so this will be useful for whenever you want to do other models, let's say any 2 by 2 model you have been given even in the exam, and you may be asked, the question may ask you to calculate the Berry curvature, okay? So this will be helpful that if you can write the Hamiltonian, okay? So let's say, so any general 2 by 2 Hamiltonian, 2 by 2 Hamiltonian as d0 sigma 0, let me write sigma 0 plus d vector and then sigma. Okay, so d0 is some d0 associated with the identity matrix, and d is some vector which have dx, which can be a function of kx and ky and kz, all k basically. But for 2D, basically you will have only kx and ky. Okay, so as 2 by 2 Hamiltonian. So there are two things. Okay, here. So this is 2 by 2 Hamiltonian means that your matrix size is 2 by 2, and another one is if you constrain it to in the 2D, then you will your k will only be kx and ky, right? If you do not constrain in 2D spatial dimension, so two spatial dimension, then you only kx and ky. If you have 3D system, three-dimensional system, then of course there will be kx, ky, and kz. Okay, but in general, you can write this dz of k. Okay, so this is just the vector, and sigma vector is simply the Pauli matrices. Okay, okay. So if you have this kind of Hamiltonian, then what you need to do is that to calculate the Berry curvature, you essentially need to take curl. This is in the K space, curl of the Berry connection, and then curl of Berry connection. The Berry connection is simply given by iota u of k. times gradient of k u of k. Okay, and this u of k is block wave function or the eigenvector of h of k. Okay, so you solve the Hamiltonian or you diagonalize the Hamiltonian, you get some eigenenergy and eigenvector, right? So u of k is just the eigenvector. So if you actually calculate this for any general Hamiltonian, so this without sort of assuming that what is the explicit form of dk, right? Dx, how dx, dy, and dz depends on the k. It is dependent on k linear, k square, and so on. It can be anything. So in general, you can show that the Berry curvature omega z, since this is a 2 by 2 system and 2 by 2 Hamiltonian, so you will have a two eigenvalues, right? So two eigenvalues will lead to two component of the Berry curvature, right? So you will take only u plus here, and then you can also take u minus here, corresponding to your energy will be plus and minus, right? So let me write down first the energy for this kind of Hamiltonian. So for this kind of Hamiltonian, the energy of plus minus can simply be written as d0 plus minus root over dx square plus dy square plus dz square. Okay, am I right? Let me think. So yeah, it is fine actually. Yeah. So for these two energies, correspondingly, you will get u plus minus of k, right? And with this, you will have two Berry curvature as well, plus minus of k, let's say. And you can show that in general, the Berry curvature can be written as minus plus 1 by 2 mod d cube. I'll explain what is mod d. D vector dot product with del kx. I'm assuming two spatial dimension. Okay, cross del ky d. Okay, so what I've assumed here is that I'm in 2D. So that means k is only having kx and ky component. Okay, so there is no kz, no kz. Okay, so if we have this, then so this is the general Berry curvature expression for any Hamiltonian. Okay, for any 2 by 2 Hamiltonian in 2D. So you can just do derive the eigenenergy, eigenvectors, and you can arrive at this equation. I mean expression. Okay. Okay. So what is the D for I mean 2D Hamiltonian H of k, let's say. Now let me number these equations. So this is, let's say, equation one. Okay. So this is our Haldane Hamiltonian, low energy Haldane Hamiltonian. Okay. And this Hamiltonian, so this general Hamiltonian, let me equation 2, and this is, let's say, equation 3. Okay. So you compare equation 1 and 2. So this is the general Hamiltonian equation 2, and this is the general Hamiltonian equation 1. Okay. So if you compare equation 1 and 2, so compare equation 1 and 2, what we have is that in our case, d0 will be 0. There will be nothing associated with the sigma 0 in our equation 1. And then dx, so dx will be what? So dx will be associated with the sigma x. So that means, so this part is the dx. Okay. So let's say I am focusing on the for the k value, k value. Okay. Okay. So we can also write this Hamiltonian more in a more compact form by doing this. So let's say xi, sorry, xi is xi, and xi is plus 1 for k value, and xi equal to minus 1 for k value. So then I'll write simply minus xi, right? So xi equal to plus 1, that means minus. And here I'll replace simply xi. Okay. Yeah. So this is the general Hamiltonian. So this part is associated with the sigma x. So this is the dx. Okay. So this will dx will be minus xi 3 gamma 0 by 2 kx. Similarly, dy will be plus xi 3 gamma 0 by 2 ky. And dz will be the whole part. So the dz will be this part associated with the sigma z. And remember, note that here there is no sigma 0. So that's why our case d0 is 0. So delta plus xi 2 gamma prime cos phi. So dz is delta plus xi 2 gamma prime cos phi. Okay. So if we have this, then we already know what is d vector, right? D vector is nothing but the combination of dx, dy, and dz. So using this, we can actually derive the Berry curvature from equation 3, this equation. Okay. So for this, what we need is that we need to evaluate the derivative of d vector with respect to kx and ky, right? So d vector is nothing but minus xi, let's call it 3 gamma 0, 3 gamma 0 by 2 to be h bar vf. Okay. Yeah. So if you, uh, yeah, that is fine. H bar vf. So this will be h bar vf. Okay, let me take the, so d will be minus xi h bar vf kx I cap or x cap plus xi h bar vf ky y cap plus delta plus xi 2 xi gamma prime cos phi z cap. Okay, so this is the vector. Now what it will have, del kx of d will simply be, so this is the only kx dependent term, so minus xi h bar vf, right, and x cap. Similarly, del ky of d vector will be xi h bar vf y cap. Okay, okay. So again, so you follow this equation. So the omega plus minus of k for, let's say, xi value. So note that there will be four kind of Berry curvature. So this plus minus on in the superscript of omega denotes that whether it is conduction band or valence band corresponding to this these two energies. Okay. Whereas xi equal to plus minus denotes that I am in the k valley or k prime valley. Okay. So don't confuse this. So we have minus plus minus plus, these are corresponding to the band index, conduction or valence. So 1 by 2 mod d cube d vector dot product. So this and this cross, right? So what we have is the del kx of d cross del ky of d, right? So this means that minus, so this, so if we actually multiply these two, what will happen? Xi square is always one, right? And h bar vf will give me xi h bar vf square, and then extra negative h bar square vf square and x cross y. What is x cross y? It is simply z cap. Okay, so minus h bar square vf square z cap. Now, yeah. So plus minus xi of k equal to minus plus 1 by 2 mod d means if we convert it to d cap, then it is simply d square, right? Mod d square. So d cap, so it will make, I'll make it plus minus, observing this extra minus, and h bar square vf square, and then d cap dot z cap. Okay, d cap dot or no, let me go back to what I was doing. So I have 2 mod d cube d dot z cap, and then there will be extra h bar square vf square. Minus is observed here. Okay. Okay. So d cap dot z cap. This will give me this particular term, right? Okay. So plus minus 1 by 2 h bar square vf square. Uh, what we'll have is that this particular term delta plus 2 xi gamma prime cos phi. Okay, and mod d cube. So what is mod d cube? The mod d cube is simply given by just the mod value and then cube of it. Okay, so the mod value will simply be h bar square vf square plus, I mean, kx square plus h bar square vf square ky square plus dz square, right? So delta plus 2 xi gamma prime cos phi whole square, and then 3 by 2, right? So mod d means there will be root half, and then it's cube. So this is my omega plus minus for a value as a function of k. Okay, so let me explicitly write. So this plus minus corresponds to conduction and valence band. Okay, I missed something. No. No, I think I missed one xi somewhere. Uh, yeah, yeah, I did. I wrote something wrong actually. Yeah. So the dy in the dy you will not have any xi. Okay. If I have written it earlier, that is also wrong. Uh, okay. So let me correct it. Yeah. So actually, the actual Hamiltonian will be something like this. So the actual Hamiltonian will look like this, minus plus, and this is plus minus. Okay, plus minus. So that means, uh, yeah. So that means that this ky term will always be negative, right? So you multiply minus to plus, it is negative, plus to minus, it is always negative. So then what you can do is that you can rewrite this Hamiltonian as the following. So sorry, somewhere else. So we'll rewrite the Hamiltonian as following. So you'll have minus 3 gamma 0 by 2. Okay, and then xi kx sigma x plus ky sigma y plus delta plus xi 2 gamma prime cos phi sigma z. Okay, so this xi factor, this xi factor extra in front of kx takes care of the negative, right? So for so this was, let's say, for uh, k and k prime values. So for k value, the xi, so in front of kx, you had a negative sign. So for k value, we are saying that xi equal to plus 1, so you have a negative sign overall. For k prime value, you had a plus sign in front of kx. So for k prime value, xi equal to, sorry, you'll have prime. So for k prime value, your xi equal to minus 1. So xi equal to minus 1, and then there is already negative. So overall, it makes positive. Whereas for both k and k prime, the ky coefficient was always plus, right? Sorry, minus. Here it was negative, and this was also negative. So that is already there in negative. So here there is no xi sign. So then accordingly, our definition will slightly change. So the minus 3 gamma 0 by 2 will be h bar pf. That is the new definition. Okay. And in dy, you will not have any xi 0. So initially I wrote xi here, but there will not be any xi. So if that is the case, so this will also modify. So this will also get modified. So then there will be an extra xi here, right? Okay. So that's what I missed, extra xi here and extra xi here. Okay. Okay. And this is actually very important. I'll tell you why it is important. Okay. So we have the Berry curvature expression, and there are quite a few important thing that we can see, important conclusion or observation. So first thing is that omega at xi. So if you do not have any let's say gamma prime term, right? So there are few observation. Okay. So assume that gamma prime is zero. Remember that Haldane introduced the gamma prime term, okay? Theoretically. So when gamma prime is zero, your omega xi of k, this is plus minus, This plus minus corresponds to the valence and conduction band. You have a xi h bar square vf square delta, right? Because your gamma prime is 0 here. And then there is whole term. So h bar square vf square kx square plus h bar square vf square ky square plus delta square 3 by 2. Okay. Okay. So if that is the case, then you see that at k and k prime value, omega of k, xi k, is opposite, right? This is opposite because xi equal to plus minus 1 for k or k prime value, right? So what really this means is that total Berry curvature, total omega, considering both k and k prime, sums up to 0, sums to 0. Okay, and this is always the case for any material actually. Okay, even when the time reversal symmetry is broken, the overall the Berry curvature in the system, sorry, this is true when the time reversal symmetry is preserved. The gamma prime, when gamma prime we are making 0, it is essentially making the system to be time reversal symmetric, because Halden broke this term, I mean break this time reversal symmetry of the graphene by introducing gamma prime, a complex hopping parameter. Okay, so when gamma prime is 0, time reversal symmetry is preserved. So gamma prime is 0 means TRS is preserved. Okay, and then total Berry curvature is 0, and this implies that omega xy or yx, which is proportional to integration over, sorry, proportional to integration over Berry curvature, so that is also 0, right? So the anomalous Hall effect is 0 for time reversal symmetric system, that we have already seen in the last class as well. Now the observation 2 is that when gamma prime not equal to 0, then omega at xi equal to plus 1 and omega at xi not equal to, I mean equal to minus 1, are not exactly opposite of each other. Okay, this was what our general symmetry analysis of the Berry curvature in the last class also tells, that if the time reversal symmetry is broken, which is due to this gamma prime term, then the Berry curvature will not be exactly cancelling each other, so that there will be finite anomalous Hall effect. Okay, so you can see this from this general expression. So let me actually make this term. Okay, so from this term you can see that this xi and this xi, there is two xi, and they will make it always plus one. So the overall, I mean overall the sign, the xi is going away. Okay, so this part will cancel in the conduction, sorry, in the k and k prime value because of xi when you sum over both the values, but then these are even in xi, so they will not cancel each other. Okay, okay. Another important point is whenever this whole term, remember this whole term is nothing but the dz term, right? So this is the dz term. So this whenever this whole term or the dz term is I mean 0, that means the whole Berry curvature is also 0. Okay, so this dz term is actually breaking the inversion symmetry of the system. Yeah, so that is the point. So any of these terms, so in the dz term, so this particular term, so if I write this, so this delta term breaks inversion symmetry, p symmetry, and this gamma prime term breaks t symmetry. Okay, so any of these symmetry, if any of these symmetries are not broken, So this is if this is zero, which is the case when time reversal symmetry is preserved, then as long as you have a finite delta term, you will have a finite Berry curvature term. Okay. If the delta is zero, which means to say that the system is inversion symmetric or the graphene is inversion symmetric, but gamma prime is finite, then also the Berry curvature individually is non-zero. So that is to say that you for finite Berry curvature you need to break at least one of the symmetries, either time reversal or the inversion. So again, this is a general symmetry relation for Berry curvature discussed in the last class. Okay. Now, what we are more focused here is the fact is this particular scenario that when gamma prime not equal to zero, the Berry curvature for both the values. Imagine you are in the, let's say, conduction band, okay, because there is also plus minus. So let's say you have a system, graphene like system where your both the values are something like this, okay, something like this, where your chemical potential lies somewhere here. So you are only in the conduction band. So omega plus is only contributing, okay, for both the value. Even then also, uh, both the value can do not cancel each other, so there can be anomalous Hall effect. So sigma ah yx not equal to 0. Okay. Now this is again this is still we are not in the I mean quantized regime, right? So what really happens is that if you change these parameters, so this dz parameter in the general Berry curvature relation, so this particular parameter, so what really happens is the following. So when 2 gamma prime cos phi is, so this is mod because cos phi can be positive or negative depending on the value of phi, uh, is greater than delta, then the conductivity sigma yx of anomalous Hall is exactly plus minus e square by h. Okay. So in this particular parameter regime, if you integrate this particular Berry curvature, okay, so you just need to integrate this Berry curvature in the K space and in the correct regime. That whenever you have this particular regime, what you essentially have is that sigma yx anomalous, which is anomalous Hall conductivity, it is not only finite but also it is exactly in units of e square by h. Again, just like the quantum Hall effect. So quantum Hall effect was quantized in units of e square by h. Here also you will get plus minus depending on the sign. Okay, and this is the quantum anomalous Hall effect. You are getting anomalous Hall effect which is quantized, but in a particular regime of parameter value. Okay, okay. So so what Halden originally showed in the parameter space is the following. So he plotted, let's say, or I could have directly shown the paper, but anyway. So this is, let's say, phi. Uh, so this is minus pi, 0, pi. So this axis is phi direction, okay, and this y-axis is delta by gamma prime, okay, and this particular value is 0. So this is 0 and somewhere here upper limit is minus 3 root 3 and minus 3 root 3. Okay. So what it they observed is the following. Oh, it's not happening. Okay. Okay. So, so this was C equal to negative. So let me highlight this part, which may be, sorry. So this particular part, okay. So this was actually C equal to -1, and if I take different color, so this was actually C equal to +1, and all the outside region. So this is this is a different color. So this is C equal to 0, C equal to 0, and so on. So what is C? C is nothing but the Chern number. So C is Chern number, and which is nothing but the Brillouin zone integration of omega uh, z sum over xi. Both the values you need to account for, okay, and decay. Okay, okay, not vector. Yeah. So if so, this is the I mean the whole Brillouin zone integration. Oh, and summed up over all the values. Okay, both the values. So so depending on the values of phi, let's say you are in the 0 to phi limit, and then there is a limit. So if your parameter regime is such that you are in this limit, so this represents the gamma by sorry, delta by gamma prime. So your Chern number will be negative. That means your sigma yx will be minus e square by h. Whereas if your the phi is within 0 to pi, and you are within also the delta by gamma prime is such that you are within this regime, okay, then your sigma yx will be plus e square by h. Okay, so this is the case of quantum anomalous Hall effect. And this was actually predicted. Uh, uh, I think I yeah. So yeah, that's true. Yeah. So this is the case of the quantum anomalous Hall effect, where and this is again finite, even if your system is in the gap regime. So so even if your chemical potential, let's say if your chemical potential is somewhere here, so this is chemical potential, that means that bulk is gapped, right? The bulk, there is no state here, but then again there can be edge like states which will conduct the electricity just like the quantum Hall effect, and you'll have the quantum anomalous Hall effect in units of e square by h. So this was the theory part, and then of course the experimentally it has been observed in many materials, including one of the recent material people have studied is that TMD, uh, transition metal dichalcogenides, and their multiple layers and so on. Okay, okay. So yeah, so I think we'll. So this was the story of quantum Hall effect. I mean anomalous Hall effect. But yeah, I think yeah. So regarding the spin Hall effect, I think we cannot cover this in a one day lecture. I think it will at least take two lectures to complete quantum spin Hall effect. Okay, so maybe I'll stop for today, and this happens to be the last lecture of topology and condensed matter. I hope I have given some insights to these lectures. Okay, yeah. So if you have any question, again, you can reach me out in email via email at sunidri@itk.ac.in. Okay, so I'm ending the lecture.